So the last lesson of Unit 9, the last subsection of 9.5, is using the cross product to find volumes of parallelepipeds. And that's basically our lesson goal. Now, what the heck is a parallelepiped? Well, it's sort of like it's a three-dimensional parallelogram. You know how many shapes have the three-dimensional equivalents? If you have a two-dimensional triangle and extend to 3D, we call that what? Is that a triangular prism? You have a square and extend to 3D, we call that a cube. You have a rectangle and you extend to 3D, we call it a rectangular prism. If you have a parallelogram and extend it to 3D, yes, I guess we could call it a parallel prism, but I guess we just give it a fancy name of parallelepiped. Well, it looks something like this. Um, it can be defined by three vectors, because that makes sense. Three vectors, 3D. We need three of them. So I'm just going to draw three random vectors. Say, I don't know, this vector here, that vector there, and that vector there. Just three random vectors. Let's call it vector u, v, w. So here we have three vectors. Now, again, it's on paper, so it looks like 2 dimensions, but it's 3-dimensional vectors. So keep that in mind. These are 3D vectors. And with any 3-dimensional vectors, you can create what is known as a parallelepiped. You just make a parallelogram out of all the pairs of vectors. Choose 2 vectors at a time and just make parallelograms. So I can make a parallelogram with the base here, and then I can sort of go up here, parallel line there, 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 parallel line in the back. So you can sort of see it makes a, well, it looks like a slanted cube, but it's not necessarily a cube because the side lengths may not be the same. The idea for today's lesson is we can actually use cross products of these three vectors here to calculate the volume. How's that possible? Well, let's go back to geometry. How do you calculate the volume of well, let's just call this a rectangular prism, even though it's a bit slanted. The basic idea is it's just base area times its height, right? We can sort of think of rectangular prisms as stacks of sheets of paper. Right? Just like how a cylinder can be thought of as a stack of disks, which is why the volume of a cylinder is the base area of a circle times the height. It's the same concept here, except our cross-sectional area is a quadrilateral rather than a circle. So we know that the volume of this guy is the base area times height. Now the question is, what is the base area and what is the height? Well, notice how the base area, if I call this the base, notice that area is just the area of a parallelogram formed by vectors v and w. Well, we just did that yesterday. We know how to find the area of a parallelogram. So this colored area, that's just the magnitude of the cross product. So I know that this guy here is just v cross w. Well, then all I need to do is figure out the height. Now, remember when we talk about heights are always altitudes like. They're always the perpendicular height. So if I want to find the height of this parallelepiped, I need to find the height that's perpendicular to the base. I need a length that's perpendicular to this base. Hey, I need a length that's perpendicular to 2 vectors. That is the cross product again. So if we were to visualize the cross product in this diagram, the cross product would look something like this. Right? So that red color would be V cross W. But we don't want all of that. No, we only want the height. So the height should only be this much here. Well, how do I do that? Well, if we go ahead and define theta as the angle between the cross product and vector u, then that's simply a component, which we did in, I think it was 9.2, maybe? I think it was 9.2. Yeah, we did components of one vector onto another in 9.2. Notice how the height here, this length here, is adjacent to the angle, so it's going to be an area, it's going to be a cosine thing. So we should know that the height here is just going to be the magnitude of u cosine of the angle between. Right? So we just substitute. We have all the pieces necessary. So what is the volume of this three-dimensional figure? What is the volume of this parallelepiped? It's the base area. So that's the magnitude of V cross W times the height, which we said was the magnitude of U, cosine of the angle between them. Now you astute students there might notice something's familiar. This particular idea, this particular formula has an interesting structure. You have magnitude of one vector times magnitude of the other times the cosine of the angle between. We have done that before. We've done that particular structure. Magnitude of vector 1 times magnitude of vector 2 times the cosine of those two vectors. That is precisely the alternative definition to the dot product of two vectors. So ultimately, we end up with this expression here. And I'm just going to go alphabetical order. The order really doesn't matter. Vector u dot the cross product of vector w. All right, so vector u dot the cross product of v and w. This quantity is known as the scalar triple product. Why is it called the scalar triple product? Well, it's called a scalar because the final answer should be a regular number, and it's called a, if I can spell triple, I'm missing the R there. It's called a triple product because it's the product of three vectors, right? It's the u dot v cross w, right? So there you go. There's our formula. There is how we calculate the volume of a three-dimensional parallelogram. In other words, a parallelepiped. So let's put it down formally as a nice, boxed area in our notes. So the title, volume of parallelepiped. So the idea is that for any three vectors, there's a parallelepiped that can be created. So I need three vectors. If vector u is x sub 1, comma y sub 1, comma z sub 1. Vector v is x sub 2, comma y sub 2, comma z sub 2. And you can probably guess what w is going to be. X sub 3, comma y sub 3, comma z sub 3. Then the volume of the parallelepiped defined by the vectors can be found by the triple scalar product, or scalar triple product. The order always confuses me. Scalar, missing the R again, triple product. And here's the scalar triple product. It's going to be vector u dot the cross, so a v cross w. Now we run into a situation. The the dot product, where ultimately, orders of operations, you use the cross product first, and then you do the dot product. The dot product may yield positive or negative answers. It's just the nature of the dot product because geometrically it's measurement of parallel vectors, and vectors can be opposite directions. But when we're applying it within the context of finding volumes, of course it doesn't make sense for volumes to be negative, so you just have to make sure that you always make sure that your final answer is negative. So even if the scalar triple product gives you a negative number, you have to know, as a mathematician, since I'm solving for volume, that the volume should be positive. So that's why typically there are absolute value bars in this, just to make sure they're positive. Now, how do you calculate this? Well, you can calculate it exactly as it looks, right? If I give you three vectors and I want you to find the volume of the parallelepiped created by them, you can take any two vectors, what you call u and v and w. They're completely arbitrary. You get the same answer either way. You take two vectors and cross them, and once you get that answer, which should be another vector, you dot it with the third vector, and then once you assure that it's positive, that is your final volume. Of course, if you don't want to do two steps, there is a one-stop shop. There's a one-step process of doing this. You can do this with determinants as well, with matrices as well. So it ends up being that if you want to do the scalar triple product in one step, it's simply going to be the determinant of the three vectors altogether. So vector u, what is that, x1, y1, z1, vector v, x2, y2, z2, vector c, x3, y3, z3. You're going to find out that the computations required for this is 100% equivalent to the computations required for this. But just like with the dot product, it is possible for the determinant to be negative, and since we're solving for volume, we always want to ensure that it's positive. So most mathematicians put a plus or minus on the outside just to ensure that it remains positive. Just use whatever version is necessary to make your answer positive. So what are some things that you'll be asked to do? Find the volume of a parallelogram, of a parallelepiped given these three vectors. Let me use the exact wording that's going to be on your assignment, just so you're not, so you're familiar with it. So the exact instructions you'll see on the homework, it will say something like this. If vector u equals, and I'm just making this up, I'm not pulling this from the text, I'm literally just making up numbers, -1, 5, 3, vector v, 2, 1, 0, vector w is -3, 0, 4. Find their scalar triple product. Notice it doesn't say find the volume of the parallelepiped, it just says find the triple product, which means if your answer is negative, leave it as negative. If your answer is positive, leave it as positive. So you got to be very careful of the instructions. If they ask for volume, volume is always positive. If they ask you for scalar triple product, it is what it is. Positive or negative, you keep as is. So this is just a straight up application, right? So what is the scalar triple product? That is u dot v cross w. So you got two choices. You can do the operation separately, do the cross separately, and do the dot product separately, or you can just do straight up the determinant all in one fell swoop. Because I'm comfortable with determinants, I'm going to do all in one fell swoop. -1, 5, 3, 2, 1, 0, -3, 0, 4. Which is equal, so I'm going to expand it upon row 1, just like what we did. So instead of ij's case, we have actual numbers. So we're going to use the actual number, -1, and then, crisscross, you subtract, delete the row and column. So you have 1, 0, 0, 4. It's always going to be a minus this number, so -5. If that number was negative, it'd be a minus negative, which turns into a plus. Then we have 2, 0, -3, 4. It's always going to be plus this number. And then we have 2, 1, -3, 0. So what is that? That is 4 minus 0, so that's -4. This is going to be 8 minus 0, so it's minus 8 times 5 is 40. And this is 0 minus, so that's going to be a positive 3, so it'll be plus 9. So what is that? That is -44, so that is -35. -35. Right, there you go. There's the scalar triple product. Again, if the question asked for the volume of the parallelepiped, the answer would be positive 35, right? Just keep that in mind. I don't want to leave this lesson with just one example, so let's just do another example quickly here. So same instructions. I'm feeling lazy. I'm not going to rewrite the whole instructions, but it's going to be the same instructions. There's going to be one instruction for the entire assignment. So let's say they gave you vector u as 1, 4, 7, vector v as 2, negative 1, 4, vector w as 0, negative 9, 18. So we'll go ahead and find the scalar triple product dot v cross w. But of course, I'll just go straight to the determinant of the matrix. 1, 4, 7, 2, negative 1, 4, 0, negative 9, 18. So expand on the first row. So we'll expand on the first row. So you use a 1. That's negative 1, 4, negative 9, 18. Minus the 4. So that's 2, 4, 0, 18. Plus the 7. That's 2, negative 1, 0, negative 9. So that is 1 times negative 18 minus a negative, what is that? Minus a negative 36. So that's negative 18 plus 36, which is going to be 18. Minus 4, so that's a 36 minus 0, that's 36. Plus 7, that's a negative 18 minus 0 is negative 18. And 18, that is 104, that is 0. Well, that's very interesting. Here we got an answer 0. What does that mean? So this is very special. I mean, that is the answer. So the answer is 0. Well, that you're done. But I want to talk about this really quickly here. That tells us that the volume is 0? That doesn't make any sense. Let's scroll back to the parallelepiped picture. This is a three-dimensional figure. How is it possible that the volume is 0? Well, if you imagine that this box being one of the sort of like collapsible, right? Imagine vector u, you're able to pivot him. So you can move vector u down, or you can move vector u up, and obviously if you move it up, the height sort of, it's sort of like a leaning building. If you move vector u up, the building leans up, and if you move it down, it flattens. So the only logical conclusion for your scalar triple product to be 0 is your 3 vectors lie on the same plane. They're all 3 vectors on the same piece of paper. This implies u, v, w exists on the same plane. So they're all on the same sort of level. The math term for that is coplanar. So this is an important idea. So I believe the question on the assignment is going to ask you, hey, here's 3 vectors. Are they coplanar? Well, to answer that question, you just do the scalar triple product. If the answer is 0, they are coplanar. If the answer you get is not 0, then it's not coplanar. It actually, a parallelepiped exists, and the volume would just be the positive of your scalar triple product. So one last simple but pretty neat geometrical application of the cross product. You can find volumes of parallelepipeds.